So in the last episode of Solve This Simplex Problem, we went through one iteration of the simplex method to come up with this next solution. And again, just reading off the table, so notice that x1 still has a bunch of garble in its column. It doesn't have, all 0 entries except 1. So its value is 0 right now, as well as s2. The highlighted columns, however, are the ones that correspond to our basic variables, our basic solution. And we saw that, the coefficient of x2 is 3 in the second row, which means 3x2 is equal to 240, which means x2 equals 80. And likewise for s1, s3, and z. And the question I posed as we ended the last video was, is the solution optimal? And the answer is no. And that is because, essentially, there is still a negative entry in the last row, which corresponds to our z row, remember. And that is because if there's a negative entry, that means that z could be made larger by eliminating that negative entry, okay? So we do have to go through the whole pivoting process one more time. So I have already copied down this table without any markings on the next page here, and we go through the process again. So the only negative entry is -8. So that means that x1 is going to enter the solution, which is what we want anyway. So then the question remains, which variable will exit? Well, we'll see when we do the algorithm here. Now, we compute our ratios, which I'm going to do in blue off to the side here. So we have 60 over 1, which is 60, 240 over 2, which is 120, and 80 over 1, which is 80. So that means we can bring x1 into this as much as 60 units and not bump any of the constraints. So I am going to highlight that row. And thank goodness we have a nice pivot. 1 is the best pivot you could ever ask for. So that means that 1 is our pivot element, and our goal is to make all of the other entries below the 1 zeros. That essentially is like saying we're plugging in that number into each equation. So that's what's happening here. So we're going to use, and again, this is called R1, R2, R3, and R4. So we're going to use R1 to convert all the other ones to 0. So we're going to, we're going to combine R1 and R2 somehow to make a new R2. We're going to combine R1 and R3 somehow to make a new R3. And we're going to combine R1 and R4 somehow to create a new R4. Okay. So looking at the numbers for R1 and R2, it looks like I have a 1 and a 2. So I'm going to take -2 times R1, add it to R2, and make a new R2. For R1 and R3, that looks really nice. I'm just going to take the opposite of R1 and add it to R3 to make that 0. And for the R4, I'm going to take 8 times R1 and add it to R4. And that'll make the 0 in that column. So just writing down these numbers. So -2 R1 would be -2, 0. I'm just going to speed through this. You can pause if you want to do this on your own. And I'm just going to draw the little vertical line here. Okay, and that be that. R2 is this. And if we add them together, we get this. Okay, so there's our new R2. Opposite of R1 is just flipping all the signs. R3. And then add. And then last but not least, 8R1. And then R4. And adding those together, we get 0, 0, 24, 9, 0, 3. And that looks like 4560. So, new R3, new R4, and good news is R4, notice, no negative entries. We are done after we put this all together. So the new final simplex tableau put in my line there. Okay, so we have 1, 0, 3, negative 1, 0, 0, 60, 0, 3, negative 6, 3, 0, 0, 1, 20, 0, 0, negative 3, 1, 1, 0, 20, and 0, 0, 24, 9, 0, 3, 45, 60. So as I said, this solution is indeed optimal because there's no negative entries in the bottom row, which means there's nothing I need to balance out to make z larger. So great, this is done. So then what is the solution? Well, first thing we'll do is highlight all the columns where the basic solution is. Notice that x1 and x2 now have only one non-zero entry in their column, so that means they're part of the solution now. S1 and S2, garble, so that means they're not part of the solution anymore. S3 is, though, and so is Z. So here's what we have. So we have S1 and S2 are both 0. It looks like x1 with a coefficient of 1 there is 60. It looks like 3x2 is equal to 120, which means x2 is equal to 40. It looks like S3 is equal to 20. And finally, it looks like 3z is equal to 4560, which means z is equal to 1520. And this is the max value. Now, I want to explore that S3 here for a moment because when we did linear programming in the past, x1 and x2 were the only ones we really cared about, right? We didn't think about slack at all. So that's basically our solution right there. But now notice S3 is 20, which means in the third constraint, whatever that was, we're going to have 20 units left over. So if I whiz all the way back up here, S3 is in this constraint, and you notice our solution, our optimal solution, has x1 being 60. So yeah, we didn't use that whole constraint. There are 20 units left over from that constraint. So the simplex method actually tells us a lot of information that way. It doesn't only tell us what our optimal solution is, but how much is left over and from which constraint. So hopefully this helps you get started with simplex method. I thank you so much for watching this 4 or 5 part series, and